0-day brief.
I want to start off today by reading something directly from the top of our briefing stack. It's a quote that kind of stopped me in my tracks.
Oh, yeah, I know the one you're talking about.
Right. It says, there is a vulnerability in Windows that requires no phishing email, no malicious attachment, no user clicking anything.
Nothing at all.
Exactly. You just have to be connected to a network, any network. Because on every Windows machine, there is a piece of code that has been silently parsing DNS responses since the 1990s, written in C, running at all times, and nobody has ever treated it as an attack surface. That just changed.
It is, it's a really chilling way to frame the situation, honestly. But looking at the technical documentation for this vulnerability, it captures the severity perfectly.
Yeah, it really does.
I mean, we are looking at a fundamental breakdown in how operating systems trust the networks they connect to.
Oh, welcome to this deep dive, everyone. Our mission today is to unpack a massive stack of research and disclosure notes regarding CVE 2026-41096.
It's quite a mouthful.
It is, but this was disclosed on May 12th, 2026, which was Patch Tuesday, and it is a truly terrifying vulnerability in the Windows DNS client. So, okay, let's unpack this. The core tension we are looking at today is that DNS, the domain name system, is arguably the most trusted protocol on Earth.
Right. It's essentially the phone book of the internet.
Exactly. It passes through every firewall, every single security boundary. But now, an attacker can turn a simple DNS response into remote code execution. And for you listening right now, whether you are working from a coffee shop, sitting in an airport lounge, or logged into a heavily fortified enterprise network, well, this deep dive is about the invisible plumbing of your devices and why it is suddenly leaking.
Right. And to understand why this specific leak is so critical, we need to lift the hood on what actually happens when your computer asks for directions on the internet.
Okay, so break that down for us.
So when your Windows machine makes a DNS query to resolve a host name, the response that comes back is parsed by a specific file called DNSAPI.dll.
And that's the code from the 90s, right?
Exactly. This is legacy C code. And, the defining characteristic of legacy C code is that it requires the programmer to manage memory manually.
Which just leaves a lot of room for human error.
Right, exactly. So the parser implicitly trusts the length fields embedded in the DNS response packet. When the response arrives, the code essentially asks the packet, hey, how big are you? And it allocates a buffer in the system's heap memory to store that data.
Okay, so it sets aside a specific amount of space.
Yeah. Let's say the system allocates a 256-byte buffer based on standard expectations. But an attacker crafts a malicious response where the actual payload is, say, 512 bytes long.
Oh, I see where this is going.
Yeah, because the parser doesn't double-check the actual size against the allocated buffer. Those extra 256 bytes don't just vanish. They spill over the boundaries of that allocated space.
And they just overwrite whatever adjacent memory is on the heap, right?
Precisely. It's a classic heap-based buffer overflow.
But the heap isn't just like a junk drawer, right? If you're overwriting adjacent memory, you're potentially crushing other critical instructions.
Yeah, you hit the nail on the head. The heap holds dynamic data, and that includes function pointers and control flow instructions. If an attacker meticulously crafts the data that overflows, instead of just, dumping random garbage in there, they can overwrite those critical execution pointers with their own instructions.
Wow.
Yeah, at that exact moment, the processor stops running Microsoft's code and just starts running the attacker's code.
That is wild.
It is. But the architectural reality that pushes this to a 9.8 out of 10 on the CVSS severity scale is the trigger mechanism, or rather, the lack of one.
Right, and that is the part that really messes with my head. Because I have always operated under the assumption that if I don't click the sketchy link in the spam email, and I don't download the weird invoice attachment, I am generally safe.
Yeah, well, that paradigm completely falls apart here. Your Windows operating system is a highly active machine.
Right, it's doing stuff in the background.
Exactly. It makes DNS queries continuously in the background without any user interaction whatsoever. It checks for software updates. It sends telemetry data to Microsoft.
Verifying certificates and all that.
Yep, verifying certificate revocations, pinging domain controllers. The machine is just an active chatterbox.
So you're saying I don't have to actually do anything to trigger this?
You really don't. An attacker does not need to trick you into reaching out. They simply monitor the network, wait for your machine's automated background processes to speak, and then they hand back the malicious answer.
Okay, but let me push back on the impact of that for a second, because let's say my machine does an automated background check, it parses a bad response, and the attacker gets code execution. Doesn't the DNS client run in a heavily restricted low-level sandbox?
Well, you'd think so, but no.
I mean, even if they get a foothold, they aren't getting system-level access to completely own my machine, are they?
See, that assumption is exactly what gets organizations into trouble. Windows architecture handles DNS differently than people expect.
How so?
The DNS client operates in the context of the calling process. It inherits the privileges of whatever application actually asked for the lookup.
Oh, wait. So if a core operating system service like, say, Windows Update, which runs with system privileges, makes the DNS query,
Then the attacker's buffer overflow executes with those exact same system privileges. They have total control of the machine the millisecond the packet is tarsed.
that is genuinely terrifying.
It gets worse, because even if a low-privilege application made the query, initial access is really just the entry ticket.
Right, they're in.
Yeah, once an attacker is executing code locally on a Windows machine, finding a secondary path to escalate privileges, like moving from a standard user to an administrator, is a trivial, highly documented process.
Wow. Okay, so if the vulnerability simply requires my machine to parse a malicious response, it sounds like the entire attack hinges on logistics. How does the attacker physically ensure they are the one handing my machine that poisoned response?
Exactly. They had to position themselves on the DNS resolution path. The research outlines 5 distinct vectors for how attackers achieve this interception.
Okay, let's go through those. What's the first one?
Well, the most immediate threat for everyday users is a compromised local router or a rogue Wi-Fi access point.
Like the free Wi-Fi at airport lounges or hotels or coffee shops.
Precisely. When you connect, the local DHCP server hands your laptop an IP address, but it also dictates which DNS server your machine must use. An attacker controlling that router simply assigns their own malicious DNS server.
So I open my laptop at the airport terminal just to check my email. My machine automatically asks the rogue DNS server where the mail server is. The attacker delivers the buffer overflow, and my laptop is compromised before I even open my browser.
It is entirely invisible to you. Now, for enterprise users who never use public Wi-Fi, attackers target the upstream recursive resolver.
And what does that mean exactly?
This involves compromising an ISP's DNS infrastructure or a corporate DNS server. This is a one-to-many attack.
Gotcha.
By poisoning a central resolver, the attacker can serve malicious responses to thousands of downstream clients simultaneously, all from a remote position.
But what if the ISP is locked down? Like, can an attacker just intercept the traffic while it's traveling across the internet?
That brings us to the third vector man-in-the-middle attacks, through techniques like ARP spoofing on local networks or BGP hijacking on the wider internet.
Okay, so how does that work without compromising the server?
To pull this off, the attacker doesn't compromise the legitimate DNS server at all. They just monitor the network traffic. When they see your machine send out a DNS query, they basically race the legitimate server to send a response.
Wait, how do you win a race against the actual internet?
Well, you don't have to be faster than light, you just have to be topologically closer to the target. If the attacker is sitting on the same local network segment or controls a router just one hop away, their fake response will physically arrive at your machine milliseconds before the legitimate response from a server hundreds of miles away.
And my machine just takes the first answer it gets.
Exactly. Your DNS parser accepts the first response, processes the buffer overflow, and discards the legitimate response that arrives a moment later.
That's incredible. We also have malicious VPN endpoints mentioned in the notes. And people usually fire up a VPN specifically to protect themselves from local network snooping.
Yeah, it's a brutal irony. When you connect to a VPN, the provider pushes its own DNS configurations to your client to ensure your traffic doesn't leak outside the tunnel.
Right.
If you connect to a shady, free VPN service, or if a legitimate provider's endpoint is compromised, well, the attacker now controls your entire DNS infrastructure.
And if an attacker can't compromise your network or your VPN, they use the fifth vector, which is malvertising.
Yes.
How does an ad serve a DNS response? That doesn't make sense to me.
Well, the ad doesn't serve the response, it forces the query. An attacker buys ad space on a perfectly legitimate mainstream website.
Okay.
Embedded in that ad is a hidden iframe, like an invisible pixel, that tries to load content from an obscure domain controlled by the attacker.
Oh, I see.
Yeah, so when your browser tries to render the page, it asks the operating system to resolve that obscure domain. The query goes out to the attacker's authoritative name server, and the attacker's server sends back the buffer overflow payload.
Wow. Okay, here's where it gets really interesting because I need to bring up encrypted DNS. I know what a lot of people listening are thinking right now. Browsers and operating systems have been pushing DNS over HTTPS and DNS over TLS for years now.
Oh, absolutely. They're huge buzzwords.
Right, so if my DNS traffic is encrypted, an attacker can't see what I'm querying and they can't tamper with the response. So I'm protected,
Yeah.
right? Or, wait, encryption is just a sealed envelope, isn't it?
Walk me through that. What do you mean?
So if I send a postcard, which is like standard plain text DNS, anyone along the route can read it or alter it.
Right. Totally exposed.
But encrypted DNS switches that out for a sealed, tamper-proof envelope. It absolutely protects my privacy in transit. But if the person I am communicating with is malicious, say, I'm talking to that rogue VPN endpoint, or my ISP's compromised resolver, they just put a letter bomb inside the sealed envelope and send it back to me.
Yep, exactly.
The encryption protects the bomb perfectly while it travels over the network.
Hmm.
And then my computer receives the envelope, decrypts it, hands the payload to the vulnerable C code parser, and the bomb still detonates.
That is a perfect analogy. What's fascinating here is that the payload is mathematically identical, whether it arrived over a beautifully encrypted TLS tunnel or plain text UDP port 53.
So the encryption doesn't matter for the payload.
Not at all. Encrypted DNS is a fantastic privacy tool, but we constantly conflate privacy with security. Encryption only limits who can position themselves to attack you.
Right, it forces them to be the actual destination.
Exactly. It forces the attacker to be the actual resolver you are communicating with, rather than just a passive listener intercepting traffic. But it does absolutely nothing to eliminate the vulnerability at the parser level.
Okay, so if the envelope doesn't stop the bomb, why didn't the mailroom catch it? We have multi-million-dollar enterprise firewalls designed specifically to stop malicious traffic from entering our networks. Why are they just waving this through?
Well, it's because of the fundamental nature of UDP port 53. DNS is the oxygen of the internet.
You have to have it.
Right, you cannot block DNS and still have a functioning network. That port is universally allowed through virtually every firewall on the planet. Firewalls allow it by default, and crucially, they do not inspect the payloads at the packet level.
Because historically, a DNS response was never considered a weapon.
Exactly, it was just a signpost.
But wait, Security Operations Centers, SOCs, they have massive dashboards monitoring DNS traffic all day long. How are they missing this?
SOCs monitor DNS queries, not responses.
Oh, really?
Yeah, they're looking for outbound anomalies. They want to see if an infected machine inside the network is trying to phone home to a known command and control server.
Like seeing if malware is reaching out.
Precisely. They look for data exfiltration, where an attacker smuggles stolen data out by encoding it into weirdly long outbound subdomains. Deep packet inspection on inbound UDP-53 responses is incredibly rare because it is computationally exhausting to inspect every single incoming DNS record at line rate.
Hold on, what about NDR network detection and response tools? The high-end platforms that use machine learning to analyze network behavior, surely they are inspecting this traffic.
You'd hope so, but NDR tools analyze metadata and traffic patterns. They care about who asked for what and when.
Okay, so if my finance server starts talking to Russia.
Right. If your finance server suddenly queries a known Russian hacking syndicate's domain at 3 in the morning, the NDR flags it. But they rarely perform deep payload analysis on the actual response records themselves.
Got it.
And to tie it back to your envelope analogy, if the enterprise is using encrypted DNS, the NDR tool cannot inspect the payload anyway without breaking the TLS encryption.
Which I imagine is a nightmare.
It is. Setting up TLS decryption at the enterprise edge introduces massive performance bottlenecks and certificate management nightmares. So the traffic just flows right past the sensors.
So we can't block it with a firewall, and our smartest detection tools can't see the payload. The only option is to patch it. But looking at the source material, the patching process itself seems structurally flawed for this specific threat.
Yeah, the researchers refer to it as the patching paradox. Let's look at which machines are in the most immediate danger. It's the roaming laptops.
The ones connecting to hotel Wi-Fi.
Exactly. The devices that leave the safety of the corporate perimeter every day to connect to untrusted networks. They are the primary targets for the local router positioning vector we discussed earlier.
The road warriors are the ones in the line of fire.
Yep. And those exact same machines are statistically the most likely to miss Patch Tuesday.
Oh, of course, because they aren't on the corporate network.
Right. Our patching infrastructure assumes devices are connected to a high-speed, highly controlled corporate environment. But when a user finishes working in an airport lounge, they don't leave the laptop open to install updates. They slam the lid shut, suspending the machine.
Or they get the update prompt during a presentation and just hit "Remind me tomorrow" for 3 weeks straight.
Exactly.
Yeah.
Meanwhile, the desktop computer, sitting safely behind 3 layers of physical and digital security at corporate HQ, the machine least likely to encounter rogue Wi-Fi, gets patched immediately.
Okay, so what does this all mean for you listening? Because Microsoft rated the exploitability of this 9.8 vulnerability as unlikely. Doesn't that mean we can all just take a breath? If the vendor says it's unlikely, maybe we don't need to panic.
See, that label has a dangerous psychological effect on IT departments. When Microsoft uses the term unlikely, they are communicating 2 very specific data points. 1, they have not seen active exploitation by threat actors in the wild yet. And 2, the technical complexity required to write a reliable exploit for this specific memory corruption is high.
Okay.
What unlikely does not mean is that exploitation is impossible, or that proof of concept code isn't actively being developed.
It sounds like corporate IT departments use that label as an excuse to hit snooze.
It absolutely gives them permission to deprioritize a critical 9.8 CVSS fix. They move it from drop everything and patch right now to, we'll push it out during the regular monthly maintenance window.
Yeah.
But we have to understand how attackers view Patch Tuesday.
Who's that?
For them, it is exploit announcement day.
Oh, wow. Because the patch itself reveals exactly where the vulnerability is hidden, right?
Exactly. Binary analysis is highly automated now. The vendor releases the patch, which effectively highlights the exact lines of code that were modified. Attackers download the patch, diff it against the unpatched version, and instantly see the previously hidden path to the vulnerability.
So the clock is already ticking.
The clock doesn't start when an organization gets breached. The clock starts the second the patch is published.
This isn't just about one missed patch, though, is it? Because looking at the timeline in our notes, this is the 4th major Windows DNS vulnerability disclosed in recent memory. This isn't just about one bug.
No, it's a much larger pattern.
It's like finding termites in your wall. You know, you can patch the hole in the drywall, you can paint over it, but if the foundation of the house is infested, patching one hole doesn't save the structure. The termites are still in the wood.
That termite analogy perfectly illustrates the real nightmare scenario here, which is lateral movement. Let's trace the path of that roaming laptop we talked about. The user connects to a compromised hotel Wi-Fi. The attacker uses this DNS buffer overflow to silently take control of the machine. The user checks out, flies home, and carries that compromised laptop straight past the physical security guards and into the corporate office the next morning.
So the termite is now inside the safe house. What happens next?
Once it connects to the internal corporate network, the compromised laptop can execute a cache poisoning attack against the internal DNS infrastructure.
Oh, boy.
Yeah. DNS is the central directory service for everything inside an enterprise. If an attacker can poison that directory, they own the namespace. When every other domain-joined machine in that office asks for the IP address of the internal file server, or the payroll application, or the domain controller itself, they receive a malicious response controlled by the attacker.
So the attacker doesn't even need to hack those other machines directly using complex post-compromise exploits. They just sit in the middle and lie to them.
Exactly. The blast radius expands across the entire domain simply by answering directory queries with mathematically crafted lies. The other machines implicitly trust the DNS response. They route their authentication tokens or sensitive data to the attacker's infrastructure, and the network falls.
Just like that?
Just like that. This is lateral movement at the foundational protocol level, completely bypassing standard endpoint detection.
Which means this isn't just a DNS problem, because if we look at the whole stack of protocols we rely on, DNS isn't the only one written in C in the 1990s.
Not at all. If we connect this to the bigger picture, we are observing a systemic collapse of protocol trust. Consider the bedrock of network communication. You got NTP for time synchronization, DHCP for assigning IP addresses.
ARP for mapping IPs to hardware.
Right, and BGP for routing traffic across the global internet. These protocols were architected in the 1980s. They were built for a nascent academic internet where every participant was assumed to be cooperative and trustworthy.
Right, the 1980s internet where everyone knew everyone. And the idea of weaponizing a request for an IP address was just absurd. I mean, think about DHCP. Your computer wakes up, connects to a network, and literally shouts into the void, "Who am I? What is my IP address?" And it just implicitly trusts whoever answers first.
And if an attacker answers first, they dictate your machine's reality. That legacy assumption of trust is now a massive structural vulnerability. Threat actors have realized that fighting through modern, heavily scrutinized application layers like, breaking out of a Chrome browser sandbox is incredibly difficult and expensive.
So they're taking the path of least resistance.
They are moving down the stack. They are systematically hunting through old C parsers at the very edge of the trust boundary. They are looking for memory corruption bugs in code that hasn't been audited in decades simply because it just works. DNS is the current battleground, but it is just one component of a much wider campaign.
Which really brings this all home for you listening. We spend so much time worrying about zero-day exploits in our web browsers, or sophisticated phishing campaigns, or malicious apps stealing our data, but the boring, invisible plumbing that you rely on every single day just to connect to the internet, the code that runs silently in the background before you even open an application, that is the new front line of cybersecurity. The attackers are moving down the stack. They're no longer targeting the windows of the house. They are targeting the foundation.
Exactly.
Yeah.
And this fundamentally challenges how we defend our environments moving forward. Perimeter security, the idea that we can build strong firewall and keep the bad traffic out, is completely incompatible with attacks that ride in on universally trusted, universally allowed protocols.
You cannot block the attack surface when you literally need the attack surface to communicate.
Exactly.
Which leaves us with a pretty intense thought to mull over as we wrap up today. If the very foundational protocols of the internet, like DNS, DHCP, and ARP, are fundamentally flawed because they implicitly trust the answers they receive, what happens when patching individual C code parsers is no longer enough?
It's a daunting question.
Are we rapidly approaching a moment where the internet has to completely rip out and replace its core vocabulary? Or do we risk moving into a reality where simply connecting to a network, any network, is an inherently fatal action for a device?
We are trying to secure a 21st century digital economy on a 20th century foundation of trust that simply no longer exists.
Well, that is certainly going to make me look at the free airport Wi-Fi connection just a little differently today. Thank you all for joining us on this deep dive into the invisible plumbing of our networks. Stay curious, stay skeptical of your connections, and we'll catch you on the next one.
Thank you for listening to ZeroDay Brief.